Welcome to SDN Tech Networking Podcast, world's first human-curated AI podcast.
All right, welcome back. For today's deep dive, we're going to be looking at something that's got the potential to be really, really revolutionary. Quantum computing. I know a lot of you out there, like me, are super curious about this whole field, but want to make sure we really get it.
It's definitely complex stuff, but it's also incredibly fascinating. We're talking about completely changing the way we think about computation itself, going way beyond what we can do with even the most powerful classical computers.
Absolutely. So we're going to break it down, explore the key ideas, and hopefully have some of those aha moments along the way.
Yeah.
And I thought we could actually start with a bit of a surprising angle. The concept of randomness in computation. You know, in our everyday tech, we see random stuff all the time, like when a computer spits out a random number.
Right.
But the thing is, most of the time, those aren't truly random numbers. They're what's called pseudo-random.
Yeah.
Meaning they're generated by an algorithm that's based on some initial value, a seed, so they're actually predictable if you know the starting point.
Exactly. That's a key difference. True randomness, like in its purest form, is totally unpredictable, even if you know where you started. And that's where quantum systems kind of enter the picture. They offer this possibility of genuine randomness. Now, we won't go too deep into the physics today, but it's important to remember that the quantum world works in ways that can lead to events that are truly random.
Yeah, it's a pretty big shift in thinking about how computation works. So we're going to start from this idea of pseudo-randomness, which is kind of deterministic in classical computing, and then we're going to move into the world of quantum and how it could harness this potential for true randomness. But let's begin with the very basics. Qubits, quantum states, and how they evolve over time.
Okay, so the foundation of quantum computing is the qubit, the quantum bit. This is like the first big jump we take away from classical computing. A classical bit is like a light switch, right?
Oh.
It's either on, which is a 1, or off, which is a 0. But a qubit can be in a superposition of states.
Superposition. Now, I've heard that term thrown around a lot. Help me wrap my head around that.
So imagine that light switch, but instead of just on or off, it can be somewhere in between.
Okay.
And it's not just a dimmer switch. It's more like it's both partially on and partially off at the same time with different probabilities. So until we actually look at the qubit or measure it, it exists in this kind of fuzzy combination of both 0 and 1. And then we have entanglement. Einstein, he called this spooky action at a distance.
Spooky action. Now, what makes it so spooky?
Well, entanglement, it links two or more quantum particles in a way that's, well, weird, to say the least. Their fates are intertwined, so if you measure one entangled particle, you instantly know the state of the other, no matter how far apart they are. And this correlation, it happens instantly, which seems to break our classical understanding of cause and effect and the speed of light, you know? Entanglement it's a fundamental resource that makes quantum computation possible.
So you measure one, and you instantly know about the other one, even if they're light years apart.
Exactly.
That is spooky.
Yeah.
And it sounds incredibly powerful. It's these properties, superposition and entanglement, that really make quantum information different from classical information.
Exactly. They open up possibilities that classical computers they can't touch. And, you know, one of the early reasons people got interested in quantum computing was this idea that, well, if nature operates on quantum mechanics, then to really understand it, to really simulate it efficiently, we need quantum computers. Classical computers, they can only approximate these systems.
It makes sense. If you want to get to the bottom of the quantum world, you need a quantum tool to do it. But we're actually seeing quantum computers being built, programmed, even tackling certain problems, right? So this isn't all just theoretical anymore.
Not at all. It's becoming real.
Okay, so we've got these qubits in superposition. They can be entangled in this crazy way, and they're existing in these delicate quantum states. How do we actually control and manipulate them to get them to do calculations?
Yeah. So it's not like flipping physical switches. In a lot of the quantum computers today, particularly the ones that use superconducting qubits, we use these incredibly precise microwave pulses to control the qubits. Imagine it like you're fine-tuning a radio dial to a very specific frequency to interact with a particular station.
Got it.
The frequency, the strength, the shape, and how long these microwave pulses last, they're all carefully calibrated to do specific quantum operations, which are like the building blocks of quantum algorithms. We call them quantum gates.
So it's like conducting an orchestra but at the atomic level.
In a way, yeah.
It sounds incredibly precise.
Yeah.
And I know there's also a lot of talk about how these qubits are actually connected within the processor.
Right. The architecture or topology of the connections between qubits on the quantum chip is really important. Different connection patterns, like something called the heavy hex lattice, influence how you can design quantum circuits and how efficiently you can run certain algorithms. It's all about making sure the qubits can interact in the right ways to do these complex computations.
Okay, so we've covered the basics of qubits and how we can control them. Now let's get to the really exciting stuff. What can these quantum computers actually do? What makes them so revolutionary? Let's dive into some of these amazing quantum algorithms.
This is where things get really mind-blowing. Quantum computers have this inherent ability to solve certain types of problems with a speed and efficiency that no classical computer, no matter how powerful, could ever match. One really striking example, and one that has big implications for our digital world, is Shor's algorithm.
Shor's algorithm, the one that could potentially crack our modern encryption methods.
That's the one. Shor's algorithm gives us a way to efficiently calculate discrete logarithms and, even more importantly, factor very large numbers. These are the mathematical problems that underlie a lot of the cryptography we use today, like RSA encryption, which protects a huge amount of our online communications. The security of these methods depends on the fact that factoring really big numbers is just way too hard for classical computers to do in any reasonable amount of time.
So a quantum computer running Shor's algorithm could change all that.
Absolutely, it could.
But how does it actually work? How does it do its magic?
So Shor's algorithm breaks the problem down into two main parts. The first part, and this is where the quantum computation really shines, is finding the period of a certain mathematical function. And for this, we use a really powerful quantum algorithm called the quantum Fourier transform, which can find these hidden patterns exponentially faster than any known classical method. The second part then takes this period and uses a classical algorithm, the continued fraction algorithm, to actually figure out the factors of the large number.
It's a team effort then. Quantum speed for the heavy lifting, and then a handoff to classical methods for the final steps.
Exactly.
That quantum Fourier transform, it sounds like a real workhorse.
Yeah, it's crucial. It's what gives Shor's algorithm its incredible speed up. It can analyze the frequencies within a function super efficiently, but quantum algorithms aren't just about cryptography. They're also showing a lot of promise for tackling really complex problems in the natural sciences.
Like what? Simulating molecules.
Exactly. We have algorithms like the variational quantum eigensolver, or VQE, that are being developed to figure out things like the ground state energy and other properties of molecules and materials. This could revolutionize fields like materials science. Imagine designing brand new materials with very specific properties just by using these quantum simulations. Then there's time dynamics simulation, or TDS, which can help us understand how quantum systems change over time. This is really important for studying things like chemical reactions and how complex molecules behave. These are areas where classical computers struggle because simulating quantum systems is just so computationally demanding.
So we could design new drugs, new super efficient materials, all at the atomic level using these quantum simulations. That's pretty amazing. What other kinds of problems are quantum computers showing promise for?
Another huge area is optimization. A lot of real-world problems like logistics, scheduling, financial modeling, they all come down to finding the best solution out of a huge number of possibilities. And for this, we have the Quantum Approximate Optimization Algorithm, or QAOA. It's a heuristic algorithm, meaning it tries to find good solutions, not necessarily the absolute best, but in a reasonable amount of time. And it's shown some real potential for outperforming classical methods for certain really tough optimization problems.
So QAOA could help us optimize everything from airline schedules to investment portfolios.
Potentially, yes. It's a new way of approaching these very computationally intensive problems. You also mentioned the Hadamard transform and the quantum Fourier transform specifically. The
Yeah.
Hadamard transform, while we haven't gone into a lot of detail on it today,
It's a pretty fundamental part of the quantum toolkit, right?
absolutely. The Hadamard gate is like a cornerstone. It's a single qubit gate that takes a definite state, either 0 or 1, and puts it into a superposition of both 0 and 1. It's like creating that initial quantum uncertainty that lets a quantum computer explore lots of possibilities all at the same time.
It's what sets up that superposition.
Exactly.
Okay. And then the quantum Fourier transform, we've talked about how important it is in Shor's algorithm. What else is it used for?
While Shor's algorithm is its most famous application, the quantum Fourier transform is much more general than that. It's like the quantum version of the classical discrete Fourier transform, which is used all over the place in signal processing and data analysis. In the quantum world, the quantum Fourier transform could give us huge speedups for things like pattern recognition and analyzing the frequencies within quantum data.
So it's not just about numbers and cryptography. It's a key tool for understanding quantum information itself.
Right.
Now, with all the excitement around AI these days, especially generative AI and large language models, I'm curious, how does all that compare to quantum computing? Are they trying to solve the same kinds of problems?
That's a good question. While they're both really transformative technologies, generative AI and large language models, which run on classical computers, they're great at things like creating text, images, understanding language. They're all about finding patterns in massive amounts of data. Quantum computing, though, it offers this fundamentally different approach to computation. It uses quantum phenomena to tackle problems that are just impossible for classical computers to solve, even the most powerful ones, especially in areas like simulation, optimization, and certain mathematical problems.
So different tools for different jobs.
Pretty much. It's not like one is going to replace the other anytime soon.
Got it.
Now, there are a couple of other interesting areas within quantum technologies that are worth mentioning. One is quantum key distribution, or QKD.
QKD, we touched on this earlier. This is another quantum security application, right?
Yes. It's a totally new way of thinking about secure communication. What makes it so amazing is that its security is based on the fundamental laws of quantum physics, which, in theory, makes it impossible to eavesdrop on without being detected.
Okay, how does that work?
Basically, QKD involves encoding information about a secret key onto single photons. These photons are then sent over a communication channel. Now, if anyone tries to intercept or measure these photons, they inevitably disturb their quantum state. And this disturbance, it can be detected by the people who are communicating. By comparing some of their measurements, they can figure out if someone was trying to listen in. And if the level of disturbance is low enough, they can then create a secret key that is totally secure.
So it's not about making the encryption algorithm itself more complex. It's about making sure the exchange of the secret key is totally secure, even against a future quantum computer.
That's the idea. And this need for future-proof security is also driving the development of quantum-safe cryptography, or QSC. This focuses on creating classical algorithms that are thought to be resistant to attacks from quantum computers. It's like getting ready for a post-quantum world.
It makes sense. We can't just wait until quantum computers become a threat to our current encryption. We need to be prepared. Now, what about the current state of quantum computers themselves? They're still in the early stages, right? And prone to errors.
That's one of the biggest challenges. Current quantum computers are pretty noisy, which means the quantum states are easily disturbed by their environment, and this can lead to errors in the computations. So researchers are working hard to develop ways to mitigate these errors. They're trying to identify, understand, and then reduce the impact of these errors to make quantum computation more reliable.
So it's an ongoing effort to make these fragile quantum systems more robust. And I imagine there's a trade-off. The more error mitigation you do, the more computational resources you need.
Exactly. More sophisticated error mitigation strategies often require more qubits and more complex circuits.
Yeah.
It's a balancing act. But it's important to remember that the development of quantum technologies is a global effort. Lots of initiatives around the world are investing in this field because they recognize its potential to transform industries and even national security.
It really feels like we're just starting to scratch the surface of this incredible field.
Yeah, it's early days, but it's moving fast.
We've gone from talking about randomness to these mind-blowing ideas of superposition and entanglement, to the power of quantum algorithms like Shor's, to the promise of quantum secure communication.
And it's all based on harnessing these incredible quantum phenomena.
Quantum computing is a totally new paradigm for how we process information.
It really is.
It offers capabilities that could lead to breakthroughs in so many areas.
Absolutely.
But it's still a young field with big challenges.
Right.
This ongoing research into things like error correction is crucial for us to really unlock its full potential.
Couldn't agree more.
So, here's something for you to think about. Given the potential for quantum computers to revolutionize so many fields, from medicine to materials science to cybersecurity, what are the long-term societal implications we should be considering right now?
That's a great question.
This isn't just about technology. It's about a fundamental shift in our computational abilities. And that could change the world in ways we can't even imagine yet. Thanks for joining us for this deep dive into the fascinating world of quantum computing.
It's been a pleasure.
We'll see you next time.